Welcome to Limitless Math. Today we're learning about the Triangle Inequality Theorem, a fundamental concept in geometry that helps us understand when triangles can actually exist. The Triangle Inequality Theorem states that the sum of the lengths of any two sides of a triangle must be greater than the length of the third side. This simple rule determines whether three given lengths can form a triangle. Let's visualize this with a triangle. We'll label the three sides as A, B, and C. The theorem gives us three important inequalities that must all be true for a valid triangle. Mathematically, this gives us three inequalities. First, A plus B must be greater than C. Second, A plus C must be greater than B. And third, B plus C must be greater than A. All three conditions must be satisfied simultaneously. If even one inequality fails, the three lengths cannot form a triangle. This theorem is essential for solving geometry problems and has practical applications in fields like GPS navigation and computer graphics. Now that we understand the basic concept, we're ready to explore the mathematical formulation and see this theorem in action through practical examples. Now we'll explore the precise mathematical formulation of the Triangle Inequality Theorem in Euclidean geometry. Understanding these formulations is crucial for advanced applications in mathematics and physics. The standard form of the triangle inequality in Euclidean geometry states that the sum of the magnitudes of two vectors A and B is greater than or equal to the magnitude of their sum. Here we see two vectors A and B. The triangle inequality tells us that the direct path from start to finish, shown by the vector A plus B, is always shorter than or equal to taking the path along a then B. The equality condition is particularly important. Equality occurs only when the vectors point in exactly the same direction. When both vectors point in the same direction, the path along a then B is exactly the same length as the direct path. This is the only case where we get equality in the triangle inequality. Now we'll introduce the reverse triangle inequality, which is equally important in advanced mathematics. The reverse triangle inequality states that the absolute value of the difference between the magnitudes of two vectors is less than or equal to the magnitude of their sum. Here's an example. If vector A has magnitude 3 and vector B has magnitude 1, then the absolute difference is 2, which is indeed less than the magnitude of their sum, approximately 3.16. These mathematical formulations provide the foundation for understanding the triangle inequality theorem in advanced mathematics, physics, and engineering applications. Here's our first example to practice the triangle inequality theorem. We want to determine if we can form a triangle with sides of length 3, 4, and 5 units. Remember, for a valid triangle, the sum of any two sides must be greater than the third side. This means we need to check three separate inequalities. Let's check each condition step by step. We need to verify three inequalities to confirm this triangle is valid. Step 1, we check if 3 plus 4 is greater than 5. 3 plus 4 equals 7, and 7 is indeed greater than 5, so our first condition is satisfied. Step 2, now we check if 3 plus 5 is greater than 4. 3 plus 5 equals 8, and 8 is greater than 4, so our second condition is also satisfied. Step 3. Finally, we check if 4 plus 5 is greater than 3. 4 plus 5 equals 9, and 9 is definitely greater than 3, so our third and final condition is satisfied. Here's the key reasoning you need to remember. All three inequalities must be satisfied for a triangle to be valid. If even one inequality fails, then no triangle can be formed with those side lengths. Since all three inequalities are satisfied, we can conclude that a triangle can be formed with sides of length 3, 4, and 5. This is actually a famous right triangle known as the 3-4-5 triangle, commonly used in construction and carpentry. Now for example 2, we'll examine a case where the triangle inequality is not satisfied. Here's our question. Can sides with lengths 1, 2, and 5 form a valid triangle? To determine if these sides can form a triangle, we must check all three triangle inequality conditions. Remember, every single condition must be satisfied for a valid triangle. Step 1, check if a plus b is greater than c. We substitute our values. 1 plus 2 must be greater than 5. This gives us 3 is greater than 5, which is clearly false. For completeness, let's check the other two conditions. Step 2, 1 plus 5 is greater than 2, which gives us 6 greater than 2. This is true. Step 3, 2 plus 5 is greater than 1, which gives us 7 greater than 1, also true. Here's the crucial point. Even though 2 of the 3 conditions are satisfied, since one condition failed, we cannot form a triangle with these side lengths. This is a fundamental rule. All 3 triangle inequality conditions must be met. Geometrically, this makes perfect sense. If you try to connect sides of length 1 and 2, they simply cannot reach across a gap of 5 units. The combined length of 3 units falls short of the required 5 units needed to close the triangle. A common mistake students make is only checking 1 or 2 of the triangle inequality conditions. Remember, for exam prep and problem solving, you must always verify all 3 inequalities to determine if a triangle is valid. Now we'll tackle a medium difficulty problem that's common on exams. This type of question tests your understanding of how the Triangle Inequality Theorem constrains possible side lengths. Here's our problem. We have a triangle with 2 known sides of length 6 and 8, and we need to find the possible range of values for the third side, which we'll call x. Step 1. We apply the Triangle Inequality Theorem. Remember, the sum of any 2 sides must be greater than the third side. This gives us 3 inequalities to work with. Step 2. Now we solve each inequality for x. We'll work through them one at a time to find the constraints on x. From the first inequality, 6 plus 8 is greater than x, which simplifies to 14 is greater than x, or x is less than 14. From the second inequality, 6 plus x is greater than 8. Subtracting 6 from both sides gives us x is greater than 2. From the third inequality, 8 plus x is greater than 6. Subtracting 8 from both sides gives us x is greater than negative 2. Step 3. Now we combine all our constraints. We found that x must be less than 14, greater than 2, and greater than negative 2. Since x must be greater than 2 and also greater than negative 2, the more restrictive constraint is x greater than 2. So we only need x greater than 2 and x less than 14. Our final answer is 2 is less than x, which is less than 14. This means the third side must be greater than 2 and less than 14 to form a valid triangle. Any value in this range will satisfy the Triangle Inequality Theorem. We can visualize this on a number line. The valid values for x are all the numbers between 2 and 14, not including the endpoints themselves. Now for our final example, we'll explore how GPS navigation systems use the Triangle Inequality Theorem in real-world applications. This demonstrates the practical importance of this mathematical concept in modern technology. Here's our GPS positioning problem. A GPS receiver needs to validate its position using signals from 3 satellites. We want to understand how the triangle inequality helps ensure accurate location data and improves computational efficiency. Let's visualize this GPS scenario. We have 3 satellites in space, each sending signals to a GPS receiver on Earth. The receiver measures the distance to each satellite based on signal travel time. Step 1. The GPS system validates the position data using the Triangle Inequality Theorem. First, we check if the sum of any 2 distances is greater than the third distance. Let's verify. 20,000 plus 22,000 equals 42,000, which is indeed greater than 21,000. We need to check all 3 triangle inequality conditions. Check 2. 20,000 plus 21,000 equals 41,000, which is greater than 22,000. Check 3. 22,000 plus 21,000 equals 43,000, which is greater than 20,000. All conditions are satisfied, confirming the position data is geometrically valid. Step 2. Understanding the computational efficiency benefits. The triangle inequality validation allows GPS systems to quickly reject invalid satellite combinations before performing complex calculations. This reduces computational overhead by 15 to 20% and significantly improves pathfinding algorithm performance. Here's the key reasoning behind why this works. The triangle inequality ensures that satellite positions form a valid geometric configuration. If the inequality fails, the GPS system immediately knows there's an error in the distance measurements and can request new data or switch to different satellites, preventing navigation errors. The real-world impact of using triangle inequality in GPS systems is significant. It validates GPS positioning accuracy, prevents navigation errors in smartphones, optimizes route calculations in mapping applications, and even reduces battery consumption in mobile devices by making computations more efficient. This example demonstrates how fundamental mathematical concepts like the Triangle Inequality Theorem have direct applications in the technology we use every day. From GPS navigation to smartphone apps, mathematics powers the modern world around us. Now that we've worked through several examples, let's address the most common mistakes students make with the Triangle Inequality Theorem and share some essential tips for success. The most common mistake is forgetting to check all three inequalities. Students often check just one condition and draw conclusions too quickly. The correct approach requires checking all three inequalities. Even if one fails, the triangle cannot exist. This systematic checking prevents errors and ensures accuracy. Another frequent mistake occurs when working with variables. Students often solve one inequality correctly but forget to consider all constraints, leading to incomplete or incorrect ranges. The correct method involves setting up and solving all three inequalities, then finding their intersection. This gives us the complete valid range for the variable. The third major mistake is memorizing the formula without understanding the underlying geometric principle. This leads to confusion when problems are presented differently or when deeper reasoning is required. Instead of just memorizing, focus on understanding the geometric principle. Visualize whether two sides can actually reach and connect to form the third side of a triangle. Here are the essential tips that will help you master the Triangle Inequality Theorem and avoid these common mistakes. First, always check all three inequalities systematically. Don't stop after finding one that works or fails. Second, when working with variables, solve all three inequalities and find where they all overlap. This intersection gives you the complete valid range. Third, always visualize the triangle. Ask yourself, can these three sides actually connect to form a closed triangle? This geometric intuition will guide your algebraic work. Finally, always double-check your work by substituting your final answer back into all three original inequalities. This verification step catches calculation errors and ensures your solution is complete. Remember this quick verification checklist for every triangle inequality problem. Check all three conditions, verify your algebra, and always think geometrically about whether the triangle makes sense. Now that we've worked through multiple examples and applications, let's recap the Triangle Inequality Theorem. This fundamental concept in geometry states that the sum of any two sides of a triangle must be greater than the third side. Throughout this video, we've seen how the Triangle Inequality Theorem applies in several key areas. First, we can check if three given side lengths can form a valid triangle. Second, we can find the range of possible values for unknown side lengths. Third, we can solve real-world problems in navigation and engineering. And finally, we can optimize paths and distances in GPS systems and other applications. Remember, mastering the Triangle Inequality Theorem comes with practice. The more you work with these step-by-step solutions, the more confident you'll become. I encourage you to try creating your own examples and explore how this theorem appears in real-world applications around you. If this step-by-step math help was useful for your exam prep, please give this video a like and subscribe to Limitless Math for more comprehensive math tutorials. Comment below with any topics you'd like to see covered next. Whether it's geometry, algebra, or calculus, we're here to help you succeed with clear, step-by-step solutions. Thank you for watching, and remember, with the right approach and plenty of practice, math truly becomes limitless. See you in the next video.